14.5 is on directional derivatives and gradients. So first we'll look at directional derivatives and how we define that. So here's the definition. And the motivation for it should be pretty clear, but it'll become more into play as we look ahead. So first, let's let W equal f of x, y. And let u equal the vector AB, where u is a unit vector. So where u is a unit vector, the directional derivative of f at a point P, so P naught, X naught, Y naught, in the direction of U is given by, so I'll define it now. I'll draw the picture here in a second. I'll define it and then we'll draw a picture of everything. But just keep in mind that this is a vector in the xy plane, 2D. This is a three-dimensional graph, right? So you have some graph, and then the directional derivative is like that. That's your u. So we're going to talk about stuff up on the graph, but your u is down in the plane. And I'll draw a picture of all that in a second, but just keep in mind when I define this. We say d, and then a subscript u of f of x naught, y naught is equal to the limit as h approaches 0 of f of x naught plus h, y naught plus h. Sorry, I messed that up. Plus h times a, and then y naught plus h times b, minus f of x naught, y naught, all over h. Now, what this does, this gives the slope of the tangent line in the direction of u. So this gives the slope of the tangent line in the direction of u. One way to define u, so I'll just say we may define u equal to cosine theta I plus sine theta j. And those will be vectors. And because that's magnitude 1, sometimes that's a nice way to define your u, but it doesn't have to be. So let's look at the picture of this thing. So draw in a three-dimensional coordinate system. Let's come down to here. Something like that. And like that. About there. So here's your x, y, and z. So then we have some surface defined by your w. So this is that generic surface that I'll draw. And let's go back through and make this dotted. This is just, so it looks like it's in back. Okay. And then what we have is, so that's the limit. So you have some vector u that's, say, pointing maybe like this with unit, and it's a unit vector. So that's my u. And then you would count off, this would be like your x naught, and then this would be your y naught. Like that. Actually, it doesn't have to be x naught and y naught, you have to be on the graph, but the u could be different. So let me expand that out. So your u, let's just say this kept going, be easier to draw it that way. I drew it as if it hit the point, but it doesn't have to. Okay, so your u is a unit vector, but it have to look something like that. Okay, then these dotted lines go here and back to your prime. So, so it is, I mean, your u is your AB, but the point is up on the surface. Okay, so just to be clear on that. So the point is up on the surface, up here. And then you get the slope of the tangent line in that direction. So you get, so here's your tangent line up on the surface, and it's that same, so there's your, that's like L. And I try to draw that as if it's in the direction of U. So that's what it looks like. That's the concept. And so you start, some direction of U, and then some point, go up to the surface, and then you get that slope of that tangent line like that for your L. So that's what it does. Now, we're not going to need to take those limits, thankfully. There's a theorem that we will all like. Not going to get into the details. That says the directional derivative of u, in the directional derivative of f of x naught, y naught in the direction of u is equal to partial f with respect to x evaluated at x naught, y naught. Let's move this over. Times a plus partial of f with respect to y of x naught, y naught times b. Or if you used cosine and theta and sine theta, you can say partial fx, x naught, y naught cosine theta plus partial fy of x naught, y naught sine theta. Depending on which one is given. So remember, that's a quantity. It's just the slope of the tangent line when you evaluate that. This is in the reals. That whole thing, once you evaluate it, is a number. It's a real number, like 5 or 2 or -3. Okay, let's look at an example. All right, so let's let f of xy equal x cubed y squared. Find the directional derivative of f at p naught, p, which is negative 1, 2, in the direction of v equal to 4i plus 3j. So we're going to basically apply that theorem up there. So we want to do the partial fx is just 3x squared y squared. Partial fy will be 2x cubed y. Now, what do we have to do next? Well, we should be looking at v, and is this your AB? Okay, answer is no, it's not. It's not your AB. Because is that a unit vector? It is not a unit vector, so not a unit vector. So now we have to unitize v that to give us our u. So let's do magnitude of v, because we're going to need that to divide. Magnitude of v is the square root of 16 plus 9, which is, oops, I was going to actually do partial of that just to make it look a little cleaner. Square root of 25, which is 5. Well, that makes it kind of nice, huh? So my u is equal to 4/5 I minus 3/5 j. All right, so you got to get u as a, you're just dividing those by 5. So now that's a unit vector, because we just, right, I mean, basically we took u and we did v and we divided by its magnitude. Okay. So now if you calculate the directional derivative of u evaluated at, actually we want to write that as an f in there, don't we? So you get f, and then it's negative 1, 2. Then we want to do that calculation. And so you have your x and y, so it's going to be 3 times negative 1 squared. And then, where am I at? And then y squared is 2 squared. And then times what? Times your a, which is 4/5. So let me get that off there. So times 4/5. Okay, now what? All right, so then it's plus partial fy, which is 2 times negative 1 cubed, times my y, which is 2, and then times negative 3/5. Okay, if you calculate all that, you get 12. Okay, so that's not obvious. So just you have to do it yourself to calculate that, but you should get 12. Okay, so the slope of the tangent line of x cubed y squared at negative 1, 2 is 12. So it's a really steep slope, frankly. That's what that's saying. Oh, and that in that direction. So in the direction of your u. Okay, so that's kind of what we're doing with that. We're going to use this for other stuff later, but we first define that. Now I want to define the gradient. So let's take a look at that. So when I look at, it's an upside down delta, looks like this. That you read that as del f or you call that the del operator. So the del operator looks like this. It's like a vector, and it's the partial of something with respect to x, partial of something with respect to y. Okay, we use that for a number of things later, and then we will be doing like partial respect to z when we get into chapter, oh my gosh, it's 16. So here's the definition of a gradient. So the gradient's basically that operator. So it's del f of xy is equal to, and you basically do the partials, but it's a vector. It's partial x of xyi plus partial fy of xyj. Or you could just write that in this form, simplified form, partial fx, partial fy. Okay, another way to look at this is like a dot product. So you can say del dot f, or f even dot del would be like your real valued function times, actually not dot, I'm sorry, it's not a dot product. That's later. It's like a product. F is a real valued function, and then these are your partials. Partial. Or you could even write that as, it doesn't matter really the order you write that. You still get, you multiply in and you still get the same thing. So you still get partial of that thing, x, and then partial of f, y. So it's a vector. It's a, we call this a vector operator. Now, using that vector operator, we can define the directional derivative of u of f of xy equal to is gradient of f of xy dot u. Okay, so think how that would work, right? That's the dot product. So go back up here, right here. Here's your u, AB, and you just do the dot product, which is the sum of both of those, AB. So that should make sense. So if you're going to remember something, this is what you remember. That the directional derivative is you just take the gradient and you dot it with your direction. Always keep in mind that magnitude of u is 1. It's a unit vector. All right, so let's look at this question. So this example often I do, and I want you to to graph it, and it's done in a certain way so you can kind of see what it's trying to say and all that. But let's just, it's a somewhat mechanical one I want us to see first. So let's let f of xy equal x squared minus 4xy, and then A, find the gradient of f at the point 1, 2. And sketch. Sketching, basically I'm going to do it in a certain way because I want you to graph the vector at the point. So we're not going to make it at the origin. All right, there was something else. Okay, B, find the directional derivative of f at that same point, of course, from 1, 2 to q, which is 2, 5. You know what? So first, just let's do the gradient. So you can just start taking partials. So partial fx is 2x minus 4y, and then partial fy is just negative 4x. So the gradient of f is equal to 2x minus 4y, comma, negative 4x. That's all you get. That's it. It actually means something significant, but for now, that's it. And then we can evaluate that. It's using the evaluation bar. Sometimes it's nice and easy to do that. At the point xy gives us, and then you just plug it in, 2 minus 4 times 2, comma, negative 4 times 1, which gives us negative 6, negative 4. Okay, and then b, we need to figure out PQ. So let's just do this back here. So PQ is terminal minus initial. So it's 2 minus 1, 5 minus 2. Just to do it, let's save a little room down here. So PQ is 1, 3. What do I got to do next when I'm finding directional derivative? What do I need to do now? Yep, got to do magnitude. Magnitude. So to do magnitude, we well, I'm sorry, we got to unitize it, so we got to take the magnitude. So let's do the magnitude of that, so we can divide by it, and that's going to be root 1 plus 9, which is root 10. So u then is PQ over its magnitude, which is just then 1 over root 10 and 3 over root 10. Okay. So then find the directional derivative of f at 1, 2 in that direction. So now we got to find the directional derivative. We got to do that directional derivative in the direction of u of f of 1, 2. So that's just gradient of f of 1, 2. Oops. Dot u. So that's going to be negative 6, negative 4, which we already did, dot 1 over root 10 and 3 over root 10. Okay, so you work that out, simplify it, and you should get negative 18 over root 10, which is approximately negative 5.7. So the other piece of this was just to graph some of this. So let's just graph. I think I'm going to need more space here. I don't know why it does that sometimes. I used to do this a lot better. Okay, and let's see. I kind of know what it looks like, so I'm going to put this in the right spot. Okay. I mean, I do know what it looks like. I'm looking at my notes. But all right, so what I wanted you to do is plot this and use those points. So you're at 1, 2, and I think we can do this to scale. Yeah, so 1 and then up at 2 is the point. And then your great, okay, we wanted to do directional derivative first. Let's see. Where was I at? Well, I know the gradient. Where's the other one? The other one was one, two, three. Oh, it's 1, 3. Here it is. Okay. So PQ is that direction, 1, 3. So you're at the point 1, 2. And then we want to do your PQ. So that's P, and your Q is up there. So actually graph PQ. So it's 1, and then 1, 2, 3. So it's up here. Okay, so there's your PQ. This being your, so I'll just label it P and then Q. So that's your vector PQ. And then your vector, your gradient vector, is pointing much the other direction. So if you start here and then you count negative 1, 2, 3, 4, 5, 6, and then down 1, 2, 3, 4. So it should be that point right there. So that point down there. 2 in blue, so I'll have to count it again. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. So this is the gradient vector from here to here. So that's the gradient of f at 1, 2. Okay, so that's, again, just some mechanics stuff we should be able to do and figure out. So next important concept is, what does the gradient tell us? So it actually is an important idea of what that is.